We are discussing particle in a 1D box and we have succeeded in so far learning about the wave functions of a quantum particle in a 1 dimensional box. And the wave functions had turned out to be sine waves, and we have seen that only some will be allowed. The wave function that we have established so far are psi of x is equal to root over 2 by L sine n pi x by L, where n equal to 1, 2, 3, 4, so on and so forth, positive integer. And we have established that this set of wave functions, well, we have normalized, that is how we got root 2 by L. We have also established that they are orthogonal to each other, that is where we stopped in the last module. And we have also shown that the first derivative is not continuous at x equal to 0 and x equal to L. So, that really is not such a stringent condition on a wave function. The next step is to understand what are the energies. Since only certain wavelengths are only certain wave functions are allowed, only certain energies will be allowed as well. So, let us see how we get to that. This here is the expression for energy for a free particle, if you remember, and this is the energy that our particle would have as long as it is inside the box, and it can be only inside the box, E equal to h cross square k square by 2m. But then we have also learned from the boundary condition that psi must vanish at x equal to L, that KL is equal to n pi and n is a positive integer. So, the obvious next step is to take this KL in equal to n pi expression and plug it in to the energy expression of a free particle. The moment we do that, the energy expression becomes E of n is equal to n square h square by 8 ml square, where n is a positive integer. What just happened? Well, quantization of energy happened. Now we are saying that only certain values are allowed, and now we should say something that we deliberately did not say while discussing the wave functions in the last module. What is n? N turns out to be a quantum number for the particle in a box, and this is the beauty of Schrodinger's treatment. Unlike Bohr's treatment, where the quantum numbers fell from the sky, quantum numbers arise naturally simply from the probabilistic interpretation of the wave function provided by Max Born. Here we see an example of energy. Like energy, other quantities like momentum, angular momentum, these are also quantized, and everything arises from the imposition of some boundary condition or the other. So, now we learn a very important lesson in quantum mechanics. We learn that quantization finds its origin in the boundary conditions, which we know arise out of Born interpretation. This is very important to understand. I have seen many students who have got MSc in chemistry, good marks and all, and they can do the math associated with quantum mechanics. But this very fundamental concept has sometimes not sunk in. Let us all be very clear about this. This is one of the founding tenets of founding principles of quantum mechanics, that quantization really arises out of boundary conditions. The moment that happens, we can breathe easy. Now our conscience is clear. We have not imported a quantum number from anywhere just to satisfy some experimental observation somewhere. It has arisen naturally out of boundary condition. This is a great revelation, but that is not all. What we see in particle in a box is that, look at the energy ladder, the separation in energies increases as you go higher and higher up. Okay? That is one thing. The second thing is, Another important observation, a zero energy is not possible, because the smallest value of n, the quantum number, is 1, and for that energy has a value of h square divided by 8 ml square, which is non-zero. This brings us to the concept of 0 point energy, and this is something that becomes a governing factor when we discuss simple harmonic oscillator. We find that a free particle, a quantum free particle, can never be at rest, and it can never be at rest because if it is at rest, it is going to violate uncertainty principle. Let us say it comes to rest, it would have come to rest at some position. So, x is defined precisely, delta x is 0, and since it has come to rest completely, the momentum is also 0, plus minus 0. So, delta x into delta px is 0, that violates uncertainty principle. Uncertainty principle, we are going to talk a little more about uncertainty principle later on when we take a break from this quantum mechanical systems and discuss the operators and demonstrate uncertainty principle nicely using the position and momentum operators. But then the thing is, uncertainty principle is a law of nature. It is a boundary beyond which one cannot probe nature. So, it is not a question of making a better equipment that will let us see something you cannot see today. We can never do it as far as the current understanding of quantum mechanics is. You cannot do better than the best. You cannot violate uncertainty principle, and that is why a free particle can never be at rest, because that would violate uncertainty principle, since it would be associated with zero uncertainties of conjugate properties. That is another important revelation from particle in a box. Right. Now let us talk about the energy gaps between successive levels. What about that? If we take any energy gap, well, right now it is Ef minus Ei, so Nf square minus Ni square. Let us say I take Nf square to be Ni square plus 1. We can work out what the gap will be. Let us keep it simple. Let us say n equal to 1, n equal to 2. 2 square is 4, 1 square is 1. Whatever it is, no matter which pair of quantum numbers you take, you get a constant. For that constant, what is the value of h square by 8 ml square if I change L? If L is increased, since L square is in the denominator, energy gap between the two chosen energy levels is going to decrease. Larger the box, smaller is the energy gap. Actually, I should not have written h nu here, that should come after another piece of discussion that we have coming up, but well, bear with me until then. We are really talking about the energy gaps. So, if L is small, then energy gaps are larger. If L is large, then energy gaps are smaller. What does that mean? If you keep on increasing the size of the box, the energy levels keep coming closer and closer and closer. So, beyond a certain value, the energy levels will come so close to each other that you cannot tell between this energy level and the next one. So, you do not have discrete energy levels anymore, rather you have a band. That would be the classical limit. So, this is another beautiful thing that comes out of our discussion. Just by changing the dimension of the box, one can go from quantum world to classical world and back, and it makes perfect sense in both the worlds. This is another point of strength, another reason why we gain confidence in this treatment. Now comes the discussion that should have come before I could write h nu. Let us talk a little bit about the spectroscopy of particle in 1D box. What is spectroscopy? Spectroscopy is the study of interaction of radiation with matter. I think we all know that. Why do we want to talk about spectroscopy all of a sudden? We are talking about quantum mechanics, quantum chemistry, because well, I end up saying this for some excuse or the other in every course that I teach because I really like it. One of my esteemed colleagues told me long ago that spectroscopy is just quantum mechanics in action. You do a theoretical treatment, it is quantum mechanics. You try to do an experiment that will manifest quantum mechanical principles, you have to use spectroscopy. So, what you see in the spectrum is what you work out in quantum mechanics. And remember, of the origins of spectroscopy, of the origins of quantum mechanics, several were spectroscopic in nature. Black body radiation, we looked at the spectrum, or hydrogen emission spectrum. So, spectroscopy and quantum mechanics goes hand in hand. So, we are curious to know what kind of spectroscopy we expect for a particle in a box. We have these energy levels. Suppose can I go from any level to any level? If I shine light of appropriate energy, can I go from 1 to 2? Can I go from 1 to 3? Can I go from 3 to 4? How do we know that? We know that by considering symmetry of the wave functions, to keep things simple. You can do it in a more complicated way as well. Today we want to discuss the symmetry aspect of it, because symmetry is another important thing that appears in nature and actually governs many properties of things. For those who are interested in learning symmetry in a better way, we did have an NPTEL course a couple of years ago on symmetry in chemistry. All those lectures are now available on YouTube. You can go through them, but it will require a little bit of preparation. It will use something called group theory. But coming back to this, now what we say is something that does not require much preparation. What we are saying is, look at n equal to 1 wave function. It is symmetric with respect to inversion, which means if I just interchange 0 and L, the wave function remains the same, psi remains psi. Look at n equal to 3, it is symmetric. So, these symmetric functions with respect to inversion are called even functions. Now, look at psi for n equal to 2. If I interchange 0 and L, what will happen? Will psi remain psi or will it become something else? I think it is not very difficult to see that psi is not going to remain psi for n equal to 2. If I just interchange this, what will it become? It will become something like this. So, this is psi 2 of x. Upon inversion, I am going to get minus psi 2 of x. So, even for this I can write an eigenvalue equation. What I can write is, for n equal to n equal to 1, 3 etc., psi n of x is equal to 1 multiplied by psi n of x. So, eigenvalue equation with eigenvalue of 1 for n equal to 2, 4 and so on and so forth, psi n of x, forgive my bad handwriting, is equal to, we said minus psi n of x. So, I might as well write minus 1 multiplied by psi n of x. So, the eigenvalue here is minus 1. So, if the eigenvalue is 1, then we call it a symmetric or an even function. If eigenvalue is minus 1, then we call it an antisymmetric or an odd function. Okay. I hope that is well understood. And one more thing, number of nodes is n minus 1, as you can see here. For n equal to 1, number of nodes is 0, for n equal to 2, number of nodes is 1 and so on and so forth. Well, let me erase what I have just written, because I have actually written on top of things are going to actually appear the moment I try to go ahead. But what we have done is we have learned what even and odd functions are, and as we will see now, the symmetry has an important role to play in determining transitions between which pair of levels is going to happen and which pair of levels is not going to happen. That is determined by a quantity called transition moment integral. Transition moment integral is integral psi 2 star mu psi 1. I think we have introduced this bracket notation already. Just to revise, what this means is this: if I write integral, well not integral, if I write psi like this, let me write psi 2, let me write psi 2. This vector with the arrow pointing towards left, this is called a bra vector, and psi 2 in bra vector essentially means psi 2 star. There is another way in which we can write, since we have written psi 1 here, let us write psi 1, and when we write it in this angular brackets like this is called the ket vector. This simply means we can say psi 1. When we write them together, something like this, bra psi 2 ket psi 1, then we together call it bracket, and this implies not just psi 2 star psi 1, but its integral over the entire space, integral psi 2 star d tau. So, what we have here is integral psi 2 star, but in this case of course psi 2 star is same as psi, because our wave functions are all real, and this entire thing is the ket vector. So, this second line actually has no meaning, it is there only to have symmetry so that it looks good. So, in the ket vector we have mu psi 1. What it means is that this is integral psi 2, I will not write psi 2 star anymore, because we know that psi 2 is a real wave function, psi 2 multiplied by mu multiplied by psi 1, and here again I will write dx. Limits will be 0 to L, because limits will be 0 to L essentially because we know that beyond x equal to 0 and x equal to L, your wave function does not even exist. So, this is the transition moment integral, and that has to be equal to non-zero for a transition to be allowed, for a transition to take place. Once again, in this course we are not going to the detail of where this transition moment integral comes from, but there is an earlier NPTEL course that we had offered on molecular spectroscopy. There we have a little more discussion on this aspect. The videos are available, whoever is interested may please have a look. Now, with this background we might as well write mu equal to E into x, that is very well known, and E is a constant. So, we take E out, and well I have to erase these as well, otherwise you will not be able to see anything I guess. So, if I take E out, then the integral has integral psi 2 x psi 1. Now, that has to be non-zero. For an integral to be non-zero, the integrand has to be symmetric. What does that mean? What is the integrand here? Psi 2 x psi 1. Suppose the integral is I. If the integrand maybe I will call the integrand I, and I am going to erase this later because I am writing on things in a place where things will come. So, what we are trying to say is this: Suppose you do an inversion and the integrand becomes minus I. What will happen to the integral? If the integral was integral I dx, that will become minus integral of I dx. But see, just because we have inverted the box cannot change the value of the integral, right. So, then we have to write integral of I dx is equal to minus integral of I dx. When will it hold? When is q equal to minus q? Only when q equal to 0. So, what we see is that for an antisymmetric integrand, the integral vanishes, it becomes 0. And so, the transition is not allowed if the integrand is antisymmetric. So, what we are saying essentially is that for a transition to take place, we want a non-zero integral, and to get a non-zero integral, the integrand would better be symmetric with respect to inversion. Now see, what is x? Is it symmetric? Is it antisymmetric? It is antisymmetric. This is brought out even better if you place the origin in between. If you say that what is now L by 2, that is 0, then from plus we will go to minus. X is definitely antisymmetric. Sorry, x in this case is actually symmetric. This is a mistake, it is symmetric. So, your next line is fine, from 0 to L, right, it is not going to change sign. So, if one wave function is symmetric, then the other has to be antisymmetric, that is the issue. So, now what does that mean? That means selection rule is that delta n is 1, 3, 5, so on and so forth. From n equal to 1 level, one can go to n equal to 2 level, it cannot go to n equal to 3 level, right. Odd to even to odd transitions are allowed. So, one can have this transition and this transition 1 to 2 and 1 to 3, one cannot have 1 to 2 transitions. So, alright, we have got some insight into quantum mechanics using this particle in a box model. Now, the question is, does it have any application? Can this model by itself be applied in some chemical system? And the answer is yes. That is what we will take in the next module. So, what is spectroscopy? Spectroscopy is the interaction of radiation with matter, and essentially it involves transition from one energy level to the other. And to be honest, we are not spectroscopy is something that is not at all new to us, because after all quantum mechanics is something that has sort of arisen out of spectroscopy. I am deeply indebted to a colleague who many years ago told me that spectroscopy is just quantum mechanics in action. All these calculations that we do in quantum mechanics is manifested in interaction of radiation with matter, because that is the only way in which you can probe the energetics of a system experimentally, and quantum mechanics is all about the energy levels and wave functions and so on and so forth. Now see, just because there are two levels, it does not mean that a transition will necessarily take place. In spectroscopy, something that is very important is selection rule, and selection rule, which tells us which transitions are allowed and which transitions are not, arises from something called transition moment integral. Transition moment integral is integral psi 2 mu psi 1, and the condition is that this transition moment integral must be non-zero. Now, I think we might have introduced this nomenclature earlier as well, but just to make sure, in case we have not, let me just do it once again. What we have written here is this. In Dirac's notation, this is called Ket vector, sorry, Bra vector, and when we write a wave functions inside it, let us say I write psi 2 in a Ket vector, Bra vector, it essentially means psi 2 star, complex conjugate of psi 2. Of course, in our case we do not really have to worry about complex conjugates because our wave functions of particle in a box are all real. This is bra vector. If you write like this, so this is psi 1 in what is called Ket vector, and what it essentially means is you can just write psi 1 itself. A lot of complicated discussion becomes simpler if one uses bracket notation. In our case it is almost trivial, we might as well write the integral, but it at least saves us the hassle of writing d tau and all that all the time. So, we will use bracket notation. But I should tell you what this means, what we have written here. When you write like that, so when you write bra psi 2 Ket psi 1, then it essentially means integral over all space psi 2 star psi 1 d tau. In our case d tau should be replaced as dx because we are working in one dimensional space. Now one more thing, it is possible that I might want to multiply this psi 1 by something or make some operator operate on something. What we have done is that we have used the operator dipole moment operator, which means basically multiplication by dipole moment. So this is what it means. But you might notice that there is an additional vertical line after mu like this, that is just to make things look good. It still means bra psi 2 Ket psi 1 Ket mu psi 1, this is what it means. This is your transition moment integral, and the condition for transition moment integral is for transition moment integral to be non-zero is what we have to determine if we want to know which transitions take place and which transitions do not take place. For that purpose we are going to use here the property of symmetry of wave functions. One can of course plug in the expressions for wave functions and do it the hard way, work out the integral, and that has to be done many times, but many times you do not have to go through all that hassle. Symmetry is a fundamental property of systems which determines many of its aspects. So, here we will see how nicely one can use symmetry arguments to determine whether this integral is 0 or not. Remember, we do not really need to know at this point whether what the value of the integral is. If that is what we require, then of course we have to work it out. But if you only want to know whether it is 0 or non-zero, we will see how we can do it nicely with symmetry. To do that, let us first recognize that all these wave functions where n is odd, this one or this one, n equal to 1, n equal to 3, these are symmetric with respect to inversion. What is the meaning of symmetric with respect to inversion? If I say this is psi 1, right. So, I write something like this psi 1. And then I invert it. So, I interchange 0 and L in this case, let us say. Then upon inversion it will remove psi 1, it will remain psi 1. That is the definition of being symmetric or what is called an even function. However, look at this n equal to 2 or this n equal to 4. What happens if I interchange 0 and L? The function is going to change shape, right. Now this is plus psi 2. If I interchange 0 and L, you are going to have a function that essentially will look like this. So, upon inversion, what happens for n equal to 2, 4 etc., where n is even, we get psi n becomes minus psi n, and that makes it antisymmetric with respect to inversion, and such functions are called odd functions. Let me digress a little bit and point out that the number of nodes remember what nodes means? Node means a point where the wave function go through 0 and change sign. So, this is not a node, this is. So, number of nodes is n minus 1. When n equal to 1 there is no node, number of nodes is 0. When n equal to 2, number of nodes is 1. When n equal to 3, number of nodes is 1 here and 1 here. So, that is something that is just there, we should know it. Now, coming back to our original discussion, how do we know whether this integral is going to be 0 or not? Well, let me write on this side so that I do not have to erase it later on. See, an integral is non-zero when let me call this I, the integrand, this one is I. So, what happens if I changes sign upon inversion? So, let us say upon inversion I becomes minus I. What happens to the integral? The integral is I d tau over all space, that becomes minus I d tau. But the issue is we are talking about a transition between two levels that cannot change depending upon which one we decide to be, which point we decide to be 0 and which point we decide to be L. Just upon inversion the sign cannot change, right. So, when will this happen in any case? If this is equal to this, we are saying that the integral cannot change upon changing sign. So, that means integral I d tau must be equal to minus integral I d tau must be equal to minus integral I d tau. When will that happen? When both are equal to 0, is not it? Say q equal to minus q only when q is equal to 0, otherwise it is impossible. So, what we learn is that this I has to be symmetric, and I here is a triple product, two wave functions and your dipole moment. Is dipole moment symmetric or is it antisymmetric? Let us not forget that we can write dipole moment as mu equal to E into x, where E is electronic charge, x is displacement, x. Is it symmetric or is it antisymmetric? Well, we have said this already, that a symmetric integrand is required for the integral to be non-zero. We are now asking the question, what about x? Is it symmetric or is it antisymmetric? What happens when we invert? X becomes minus x naturally. So, x is definitely antisymmetric. So, now when will this triple product be symmetric? So, we are doing inversion, right. We take this and do an inversion. When we do an inversion, x changes sign, x becomes minus x. Let us say psi 2 is symmetric. So, psi 2 will remain psi 2. Now, if psi 1 is also symmetric, what will happen? Then this triple product changes sign, which means the integral changes sign, which means the integral is 0. How can one avoid it? Only when psi is antisymmetric. So, if psi 2 is symmetric, psi 1 would better be antisymmetric. Sorry for my horrible handwriting. Then what will happen is that due to x you have a minus sign, due to psi 1 also you have another minus sign, and the whole thing becomes plus. So, what we are saying is that if one wave function is symmetric, the origin or the destination, then the other, the destination or the origin respectively, has to be antisymmetric. That is the condition for the transition moment integral to be non-zero. That is the condition for the transition to be what we call in the language of spectroscopy allowed. So, the selection rule then is delta n equal to 1, 3, 5, so on and so forth. Why? Because if you remember the wave functions, alternate wave functions are symmetric and antisymmetric. N equal to 1 symmetric, n equal to 2 antisymmetric, n equal to 3 symmetric again, n equal to 4 antisymmetric once again. So, delta n equal to 2 can never happen. What happens if I want to go from say psi 1 to psi 2? Psi 1 is symmetric, sorry psi 1 to psi 3, psi 1 is symmetric, x is antisymmetric, psi 3 is symmetric. So, psi 1 x psi 3, the whole thing is antisymmetric. So, that integral vanishes and that transition is not allowed. Now, if you want to know where this transition moment integral comes from, that requires a little more of quantum mechanics. In fact, we have discussed it in some detail in an earlier course that we had floated in on NPTEL, a course on molecular spectroscopy, a physical chemist perspective. So, whoever is interested in knowing more about where transition moment integrals come from can go through those videos of the course, of that course, which are now freely available on YouTube, I believe. But for the purpose of this course, at least for now, we are going to take this transition moment integral business axiomatically and we are going to proceed from here. So, doing that, what we have learnt is that for a particle in a box, delta n has to be 1, 3, 5, odd to even to odd transitions are only allowed. Which means that you can have this transition 1 to 2, you can have this transition 1 to 4, but you cannot have this transition 1 to 3. Why not? Because as we said several times, 1 and 3 are both symmetric, making the triple product, which is the integrand of transition moment integral, antisymmetric. So, this is the discussion we wanted to have on spectroscopy of particle in a box, and this is what tells us which transitions take place and which transitions do not. With this background, we are now prepared to go ahead and talk about color, and we are ready to talk about whether or not there can be some application of this simple particle in a box in real chemical systems.